Hello guys, my name is Sandip. I'm a physics teacher at AskIITians. Okay. So, in the previous two sessions, if you do remember, we have completed the chapter sound, right? One session is left. Very small part of the chapter is left actually, right? So, first of all, let's recap what we have studied already. So, sound is made up of what? What is the type of wave? It's a longitudinal or transverse, right? It's a longitudinal wave. Also, I can say it is a mechanical wave, right? Longitudinal is again the part of mechanical wave. So, why it is mechanical wave? Because it needs the medium, you can say, to propagate, right? So, sound cannot propagate through the vacuum. So, we have seen that in the previous session also that at the sun there are, let's say, many explosions are taking place, but we cannot hear those, right? We can get the light from the sun, but we cannot hear the explosions. Why it is happening? Because sound cannot travel through that vacuum, right? Okay. Then we also studied that infrasonic range, then audible range. So tell me, what is the audible range for human ear? Right? Try to recall that. That is 20 hertz to 20,000 hertz, we can say, right? Or 20 kilohertz, right? So this is the audible range. So frequency or any sound which is in between these two, we can hear those, right? Then what are the ultrasonic waves? Who produces them? We particularly saw one bird there, right? Small bird, we can say. That is called as bat, right? Bat produces the ultrasonic waves, and that's how he understand where is the object, where is the obstruction, how to fly like that. Okay, and using the same principle, we have also seen that sonar, right? Sonar instrument was also there, right? So, and another type of the range is infrasonic wave. So all these three waves, or we can say frequencies we know, and obviously our audible frequency, we should know that audible frequency. What is the audible frequency? Then we also seen one part that our sound also reflect like same normal, same as that of our light, we can say, as the light reflects from what? Mirror. Sound also reflects. It even does not need the mirror. It can even reflect like this. Okay. But so if it reflect, can you hear the sound twice? Right. I'm now speaking. Obviously, some wall should be in front of me or laptop in front of me. Is it getting reflected? Yes, obviously it is getting reflected. So why I'm not able to hear two sounds? Right. That depends on the distance, right? Or something related to echo, right? That also we are going to see in this session, right? You must have heard the echo many times, right? Right, when you go to the tree or trek in the mountains or valleys, then you can hear the echo. There are points called as echo points where you shout your name and you get the reflected sound of your name, right? So obviously you must have understood that there must be some condition like valley, then only you can find out the echo, right? So in this session we are going to see what is that exact condition is. Okay, good. So then we also studied the multiple reflections and what are the applications, right? The ceiling of the theater, you can say, is not normal, not flat. It is a curved, we can say, right? Curved part is there, like that. So we know all these things. So first of all, moving to today's session or topics, I want you to solve one question. So the question is, the sound wave travels at a speed of 340 meter per second. Now we have seen at room temperature it is 346, or sometimes they will give you 330 to 340. Obviously dependent on the temperature also, right? We know if the temperature is high, the speed becomes higher. Right? So normally we do take the speed of the sound as 332 or 330 or 340. So 340 makes the calculations easier, we can say. So we can say the speed of the sound is 340 meter per second. And the wavelength, if you do remember, what is the wavelength? So the wavelength means the distance between to crust. This is crust, right? And what is this? This is trough. Now, even though we actually know that this is the transverse wave, and longitudinal is wave is what? It is made up of compression and rarefactions. Okay? But just now, just assume that our wave would look something like that, because it is easier to show wavelength where is the wavelength and etc. So wavelength means, can we say the distance between these two crust, or in longitudinal case we can say distance between two successive compressions. So this is the wavelength represented by what? Lambda. We also know that thing. Okay. So that lambda is given as 1.5 centimeter. Okay. Now the problem is 1.5 centimeter. So how much is it? It's, yes, you can see it on your scale. So 1.5 means, if this is your scale, consider this is almost 1 centimeter. This is 2 centimeter, right? And let's say these are half. So this is 1 2. So can I say the 1.5 centimeter is something like this? So this will be the wave. This is the wave they are given. So using this, we want to calculate the frequency of the wave, and the important part is, will it be audible? Or obviously human ear they are asking, right? So how to find out that? We know three types are there. Infrasonic, then ultrasonic, and third one is our audible range, right? Infrasonic, who can hear the infrasonic waves? We have seen that elephant can hear the infrasonic. Ultrasonic, dolphins can hear the ultrasonic wave, right? Then bat can hear the ultrasonic wave, right? Then we have seen that whales communicate through the infrasonic wave. Remember, whales and dolphins. So in case of fishes also, whales can hear the infrasonic waves, and dolphins can actually hear your ultrasonic waves. Okay. Good. So first of all, we will calculate the frequency, and we will see whether it is in our which slot. Is it in our 20 hertz to 20 kilohertz slot? If it is like that, then yes, then we will say it is audible. Okay, so let's calculate the frequency. What is the formula? Simple formula. We know that velocity is equal to, let's say f. Let's say f is given as, sorry, f we want to calculate, right? Velocity is given as 340 meter per second. And I know the formula v is equal to ef into lambda. Then one more thing that remember in physics, this is a very important part. Whenever you are doing the calculations, the units should be in the same system. Same system means what? If you are using the meter per second for velocity, lambda should also be meter per second, right? Like that. Or you can convert the velocity to the centimeter per second, like that. So if the lambda is 1.5 centimeter, how to convert centimeter into meter? So we know the easy calculations there. So let's say 1 meter, let me write it here. So 1 meter is equal to 100 centimeter, right? I know this part. So 1 centimeter is equal to, can I say 1 by 100 meter? That's right. So let's write this as 1.5 divided by 100 meter. Okay. So now you can see velocity also have the meter in the unit, and our lambda, that is wavelength, is also in meter. Now let's use this basic formula. V is equal to f lambda, and we have to find what? Frequency. So if V is equal to f lambda, what I can say, f becomes V upon lambda. What is the value of V? That is 340. What about lambda? Lambda is given as 1.5 upon 100. Simple. So let's do one more calculation, modification in lambda here only, right? What I can say, can I say this is 15 upon 1000? So what will happen? That will take care of the units, right? It will be easy. Sorry, decimal points, right? So we can just move one decimal point and just add 10 downwards. So instead of taking 1.5 upon 100, let's take it as 1.5 upon 1000. Now remember, this is my basic division line, right? So I can write this as 340. The main division line converted into the multiplication sign, and whatever is, this is 15, right? Not 1.5. Yeah. Whatever is below that main division line, reverse it. So that will become, let's say 1000 divided by 15. Okay, now let's try to solve this question. So this will become, let's say 34000 divided by 15. Do we know the formula, sorry, table of the 15? We should, right? So if you don't remember the table of 15, you should try to memorize it, right? And if you don't remember, obviously we can do our normal calculations also, right? So let's say 15 twos are 30, remainder is 4, that is 40. So again, what we can say, 15 twos are again 30, remainder will be 10. 10 and 100, that will become, let's say 100. Then we have 15 6 or 90, then 10. So this keeps going and you will get something like this, 22,666.666666 hertz. Okay, now look at our range. Our range is 20 hertz to 20 kilohertz, or I can say 20 hertz to 20,000 hertz. Oh, so if this is the range, tell me if this frequency is in the range or not. Obviously, it is out of the range. So it is ultrasonic. This becomes ultrasonic now. So if this is ultrasonic, can we hear it? No, right? So can I say it is not audible? It is not audible. Good. So this is how you can solve the questions, but you need to know the range and one basic formula for that. Okay, good. Sure. So now let's see what we are going to cover in this session. First one is the interference of wave. Then we are going to cover the structure of human ear. Now we already know how the sound is get produced. How? Because the particles disturbs the adjacent particles. That is our normal nature, right? Okay. So how we actually hear that sound? Can human brain process the sound? Can human brain process the vibrations? Can you imagine that vibrations, whatever vibrations are there, that going into the brain and brain will start to vibrate? Is it happening? No, right? So there must be something in our human ear as an instrument, you can say, right? Or a part of our body, which is doing some magic there, right? Okay, so what is that magic we are going to see? Then interference of waves. What is interference of waves means? So now we already know about the wave longitudinal and compression, but for the interference of wave, let's consider our this normal wave, because this is easy to understand, easy to look, right? Crust and this have crest, not crust actually, crest and troughs. So now this is one wave. Now obviously we know there will be many number of waves, right? Some are the light waves, UV rays, extra waves, sound waves, this wave, those waves. So all those waves can intersect, right? Interfere, we can say. Interfere means what? They are coming together like this, right? So one wave is coming from this side, other wave is coming from this side, and something should happen, right? So there must be some collision. What is happening in that case? So that is what we are going to see. So let's see. So here you can see the first wave. First wave, we are keeping the first wave as it is, and let's say second wave is moving. This is standing wave. Yeah, this the standing wave is also one of the type of the waves, right? It just stands. Actually, it circulates, not circulate, but it vibrates actually. But let's assume that first wave is standing now, stationary, and the second wave is moving like this, right? Now here you can see this is the crest part. This is the crest part, and this is trough part, right? That we know. Now, what should happen if the crest of the second part, we can say, comes in straight line of the crest, right? So here you can see this crest part is coming in the straight line, right? Whenever that happens, you can observe this is the, let's say this is the resultant wave. This is called as resultant wave. So you can see when the crest and crest are coming together, that the resultant waves crest becomes very high, right? Now this part is also called as amplitude, right? So remember, if this is the crest, right? The maximum height, we can also call this as amplitude. Now that amplitude you can see for the resultant wave is becoming very high. Why? Because we are actually, we can say we are adding those to amplitude. All right, amplitude because of the first wave and amplitude because of the second wave. When we add those two waves, then we get the maximum amplitude for the resultant wave. Right. Similarly, consider the another case. This is the crest of the first wave again. Right. So first crest, second crest like that. And now consider if the troughs come in between. Now this is the trough of second wave, right? When the trough comes there, what is happening? You can see that amplitude of the resultant wave becomes zero. Why? Because crest and trough, it is just like adding and subtracting. When crest comes together, it is adding. When crest and trough of the second wave comes together, it is just like a subtracting. Right? So after subtraction, we are not going to get anything into the resultant wave like this. Okay. So this is how you can see this. So this is the interference. Now let's see. Here, there are two types of interference. One is constructive, one is destructive. Constructive, obviously, the name, as the name suggests, we can say constructive means what? That amplitude goes maximum. Destructive means what? If the amplitude becomes zero. So now consider there are two waves, one like this, one like this. Now consider they are stationary, they are not moving anywhere. Okay, so here the crest of the first wave and this crest of the second wave, similar, they are together, right? So can I say, you can see that black point they are showing is always together, right? Also this orange point represent the trough. So what is happening to the amplitude? Amplitude, you can see here the amplitude of 1, here is also 1, both get added and we got the resultant amplitude as 2. Right? Okay, same thing for trough also. You can see trough was which one, which point? That orange point, right? So let's see, they will show you the orange point and let's find out when the resultant wave where that orange point goes. So here you can see orange point, trough and trough, so both are downward, so orange point will also go downward. So this is a constructive interference. When, so what I can say, crest meets crest or trough meets trough, it gives us maximum amplitude. Okay, crest meets crest and trough meets trough, we get the maximum amplitude, that is called as constructive interference. Now let's talk a little bit about the destructive interference. So here you can see this is crest of the first wave and trough of the second wave. So crest of the first wave and trough of the second wave are coming together. Similarly, here also you can see trough and crest are together. What is going to happen? Observe that green point. Let's observe the green point, amplitudes, maximum amplitude point, right? What is happening? It is at top, it is at bottom. So add these two. It is just something like adding positive and negative. What will happen if you add positive, negative? It will become 0. So my answer should be 0. Okay. Again, this is 0, this is 0, add these two, again we will get 0. So every point is going to give you 0 amplitude or minimum amplitude, right? So final result of this is for destructive we are not getting anything, that's just a straight line, and constructive interference means we are getting one bigger wave, we can say, right? So for destructive, what I should say, crest meets whom? Trough, and trough meets crest, and resultant is minimum amplitude, or in this case even we can say zero amplitude, there is nothing. Okay, so crest meets trough and trough meets crest. Simple. So this is called as destructive interference. So why we are using this constructive and destructive interference? Yes, it also works similar in case of light as well as sound, right? So consider there are, if you keep the two sources, but there are again we can, one more terminology here we can use, that these two waves are in phase and these two waves are out of phase. So if you use the two sources of the sound which are in phase, you will hear the maximum sound, right? And if you use the two sources of the sound which are out of phase, you are going to hear minimum sound, or we can say no sound, right? There is also one experiment for this. Now for experiment is something like this. So consider how to make the waves in phase or out phase, right? So this is the ear. Ear means we are listening from this side, right? And consider this is, we keep the alarm clock here. 12396, we know that, right? This alarm clock is ticking, or we can say, let's say its alarm goes off, right? This is the one tube. Let's call this as first tube, and there is another tube like this. But the another tube is adjustable. Adjustable means we can actually change the distance. Adjustable tube, right? So now consider if the length of the blue tube and red tube we are keeping same. So can I say 1 is equal to 2 length, right? So this part and this part is same, right? Then we can say they are in phase, right? So what will happen? We will be able to hear maximum sound at the ear. When they are in phase, it is constructive. It gives maximum sound. Now consider in second case, what we are going to do? We are going to shift, let's say, this red tube a little bit. Use the different color. Yes. So suppose now we are shifting this red tube like this. So now what you can see, this red part has become more, right? So in this case, I can say 1 is not equal to 2, or second is bigger. So it is out of phase. Now again, it requires a lot of conditions, how much distance you should move, because there is some particular distance which is dependent on the wavelength of that, we can say, sound or wave. So this is destructive interference, and even though alarm is ticking, we will not hear any sound, no sound. Why? Because length is changed. Again, consider if you are moving that tube again outside like that, then again they will become in phase. So it is not required that they should always be same. First and second is always same, but there must be some particular difference between the lengths of those tubes. Then only we can hear the sound. Otherwise, no sound. Right. So this is the constructive and destructive interference. Now let's talk about the echo. So echo is what basically when you go to the trek in the mountains, there must be something like echo point where you will find that many people are shouting, right? And you are also going to do that same thing, right? Why? Because you want to hear your own echo. So how to do that, and how it is happening, and why it is not happening with us right now, right? Sound is anyway reflecting from our wall, next wall. Why we are not able to hear echo? So now remember, very important thing, that human ear needs the time interval of 0.1 second. So human ear needs the time interval of 0.1 second. right? Let me write it correctly, right? To distinguish the sound. What is the meaning of that? Distinguish the sound means what is happening? Consider now you are sitting in your room and the wall is in front of you. Right now you shout like this. Yo is shouting yo, I guess, right? So shout like this. Now some the sound is going to take some time here. Let's call that as T1, right? So it will reach to your wall in front of your room, in front of you in the room, and again it is going to come back, right? So what I can say, let's say for coming back it takes the time T2. So remember this T1 plus T2 should be greater than 0.1 second. Then only you will be here to echo, right? So now consider your wall in front of your room is how much? Hardly 3 meters, or max if you have a very bigger room then it will be 4 meter, right? So and what is the time taken by sound to complete the that distance? 3 meters. So let's say consider 5 meter. Let's consider the maximum. So it wants to go 5 meter and comes back 5 meter. So total is 10 meter. And we already know the speed of sound. Let's take it as 340 seconds. Speed of sound is how much? 340 meter per second. Your distance is 10 meter, right? Actually it is 5 meter, but it also wants to come, right? So let's say this distance is d is equal to 5 meter. We are taking the very big room. 5 meter is very large distance for the room, we can say, right? So how much time it will take? So we already know time taken is what? Distance upon speed. That will become 10 upon 340 or 1 by 34. If you calculate this, I don't think it will be greater than 0.01. So 0, 0, then almost 3. And what we said, the time should be greater than 0.1. This is only covering the whole distance. It is coming back in 0.03 second. Human ear cannot distinguish. So yes, you are getting the reflected sound, but human ear, so we cannot distinguish those sound. So what is the necessary condition for this? Let's see. So how much distance should be there so that time will reflected ray will take 0.1 second. Let's see that. So now what we will do, let's try to solve this question. We need the total time as what? 0.1 second. So how much is the distance covered? So consider this mountain. From this person to mountain, what should be the minimum distance? Let's call this as d. Okay. So what should be the distance covered if the velocity of sound is how much? 340 meter per second. We also know that distance covered is 2 times, sound is traveling 2 times, right? So let's take this distance as 2d, right? So even though the distance is d between this person and the mountain, we are going to say that now sound have to cover the double distance. And what is the formula we want to find this? Formula is same. Distance upon what? Speed, right? Distance upon speed. So instead of distance, can I say distance is 2d now? Right? So this is the distance. Distance is not only d. Or let's find out the first of all formula. Write down the formula for distance is equal to speed into time. So this is 2d is equal to speed is how much? 340. Time is 0.1 second. So it will give me answer 34, or d is equal to 34 by 2, that is 17 meter. So what is the minimum distance it should have to get the echo? That is 17 meter. Then only he will be able to hear echo. Okay. So remember that point. Then you will say that opposite building, if you look through the window and opposite building is, yes, it is 17 meter or more than 17 meter. Why we are not hearing the echo? In case of building or in city, we can say there are many reflections between, many obstructions are also there in between the buildings, right? And sound actually get absorbed by the that all those things, right? Many noises are also there. So therefore that reflected ray actually do not have that amplitude to come back, right? But in natural place like this, there is no obstruction. Sound can directly travel and come back. Therefore, we hear the sound there. Okay, so remember. So is it necessary that 17 meter is the maximum or minimum distance? Right? We can say it should be the minimum distance. So doesn't matter if this distance is even 30 meter or 50 meter, still you are going to hear the echo. Okay. Obviously, time will vary in that case. Right? So this is about echo, we can say. Now, let's move to the next part, that is our human ear and how we are able to hear the any sound, right? As earlier we discussed that our brain is not vibrating, right? Okay, so how we should be able to hear the sound. So what is happening actually? Whatever sound you are is coming to your ear, right? So sound is coming in form of vibration, right? Like this, we know that part. This is the visible part of our ear. It's called as outer ear. So that's not a difficult thing to understand. We all can see which part is the ear. Now, what is inside that we know. We don't know anything, right? Okay. So what happens? Whatever sound, whatever vibrations are coming, those are going into the ear canal. Now this part is called as ear canal. Water canal you must have heard, right? So it is similar to that, ear canal. And it is just the passage, we can say, so that the vibrations can pass. Okay, and it reaches to eardrum, right? Also remember this part is called as pinna. This part is called as pinna, outer part, right, where the ear canal start, we can say. And this part here, it is called as eardrum or tympanum, they are saying, right? Okay, so just let's it is eardrum. What is eardrum? We already know drum. What is drum? When we use the drums, right, to create the music, right? That is drum. So it has the stretched membrane, right? If you know that drum, you're sounding that drum with the, what we can say to that drum. Drums, normal drums, we can say those for a music creation, right? Those drums. If you observe those are actually what? Those are stretched membrane, and on that we are actually putting those hammer-like things, not hammer, but our musical instrument, whatever those are, right? Okay, similar to that, eardrum, something eardrum like will be there, and whatever vibration we are getting, right? That vibrations are also creating some that same thing like an instrument, musical instrument, right? Those bars, those sticks are there. Yeah, sticks, we can say sticks. We are just when put it on the drums, right? Then we are getting some sound. Same thing is happening here also, right? Okay. Then those vibrations are recorded, let's say, on this drum. Then it is malus. There is another part which is called as malus. So first of all, let's see, this is the outer ear. This part is called as outer ear, obviously. Then this drum, then whole this thing is called as middle ear. So let's see what is there in middle ear. So in outer ear, can we say there is a pinna is there and ear canal is there. And what is in there in middle ear? Eardrum is there. Then we have malus. Malus is similar to, let's say, hammer. Therefore, they are saying it is hammer, right? So obviously, whatever vibrations that eardrum is taking, it will give it to the hammer. And what is the job of hammer? To give it to the anvil. Anvil means what? Now, the simple meaning of the anvil is something like that. Right. So there is a big hammer. You must have seen this anvil thing in places where they actually reshapes the iron and etc. Right? They build that iron parts. Right. So they keep some material here and hammer it with this hammer, you can say, right, to rebuild or reshape those iron material, right? So this is called as anvil. Anvil is like a base part on which you can hit by the hammer, right? So it is something like that, which is called as incus. So whatever vibrations eardrum is giving to hammer, hammer will hit it on anvil or incus, and that will be provided to stirrup or shapes. The stirrup are what? Right? The stirrups are, you can consider they are used something like that, something like this shape. You must have seen this kind of shape to the horses, right? I don't know how to draw the horse, but just consider for the horses we can use those stirrups there, and which is called as steps. So what is the job of that middle ear? There are three parts we can say in middle ear, or four parts. One is eardrum. Eardrum is taking the vibrations from ear canal, then giving it to the hammer. Hammer is giving that to the anvil. Anvil and stirrup, both job is to transfer those vibrations to the inner ear. Now this part is called as inner ear. What is that inner ear is doing there, right? So this is the important part, right? Cochlea we can say. So what is the job of that part? Then to convert all those vibrations. Remember, part of this inner ear is to convert vibrational waves or our longitudinal waves, you can say, into electromagnetic wave, or you can say it is something like a electric signal, electromagnetic waves. Then these waves will be transferred by this station tube to the brain, and then brain will understand, yes, that sound is there, right? So as I said, vibrations are only up to this part, up to middle part. The inner part, inner ear, is going to convert that vibrations into electromagnetic waves, and then those waves are going to get transferred to our brain, and then brain will analyze, yes, there is some sound coming. Okay, so that is the structure of the human ear. What you have to remember, there are three parts. First of all, outer ear, middle ear, and inner ear. In outer ear, what are the parts? Ear canal is there, pinna is there, and through inner canal, vibrations are going. What are the parts in the middle ear? Eardrum is there. Then malus means hammer, and incus means anvil, right? And stirrup is also there, right? Which is also called as steps. So these four parts you should remember, which are in the middle ear. Then now we have inner ear, cochlea, you can say, right, which actually converts the vibrational wave to electromagnetic waves. And then eustachian tube take it to brain. Okay, so this is the simple structure of our human ear. Okay, sure. So this is the whole part of our sound session. So in this topic, this is the whole chapter actually. So we have already seen how the waves are, sound is produced because of the vibrations, right? And today we also seen a little bit about the echo, and we also know about how the human ear actually works. Okay, good. So let's see some questions there. So first question, it receives the sound vibration and passes to eardrum. It means whom? Who receives the sound vibration and passes to the eardrum? Can we say that canal is passing the vibrations, right? Canal is not there, but we can say canal is the part of outer ear. So our option should be outer ear. Then border between the middle and inner ear is formed by. So let's see who is forming the border between middle and inner ear. So this is the inner ear, this is the border, right? So what we can say, this is the middle ear, inner ear. So can we say incus? Incus is providing the border there. Yes. Right. So pinna is obviously outward. Then oval window is not there. Tympanic membrane is that this one, tympanum, right? It is eardrum anyway. So we can say incus will be our answer. Now let's solve this question of the echo. What is the question? Man standing in a valley between two parallel mountains fires the gun. Okay. So let's see. Let's draw a diagram. I told you in physics, what is important? Diagrams are very important, right? So these are some mountains, and man is standing here. Not exactly in the middle, but must be somewhere, right? And fires the gun and hears a echo and at an interval of 2 seconds. What is the distance between two mountains? So actually we want to calculate this distance. So now man is standing here. So can I say, let's say this distance is x1, or let's say d1, right? And this distance is how much? d2. So time taken by echo, right? They are saying echo. Echo for, let's say, to this for this echo is 2 seconds, and let's say this is 2 seconds. No? We write it 2 seconds, and this is 3.5 seconds. Right? It's then. So we want to calculate x, or let's say total is d. So one thing I am very sure that d is equal to d1 plus d2. How to calculate d1? So for d1, we already have seen the formula d1. Our distance is equal to what? Speed into time, right? So let's say d1 is equal to speed into time. I haven't given the speed of the sound. Let's take the speed of the sound as 340 meter per second. So this is 340. Time is how much? 2 seconds. So can we say this is 680 meter? D1 is how much? 680 meter. Let's calculate the D2. Again, formula is same. Speed into time. Speed is again 340. This is 3.5. So how to do this calculations? I think this will become 170 into 7. 9, 4, and 11. So this will become 1191 meter. Okay, how actually I did this calculation? 3.5 is I converted that to 7. I didn't did anything. Suppose I consider this by I multiply this by 2 and I divided this by 2. Right, so whole effect is going to be same. So that actually makes my calculations easier. So instead of doing this 340 into 3.5, it was easier for me. Right? Okay, like this. So we got the two distances. Chalo, let's put it in our substitute in our formula. So D becomes what? D1 is 680 meter plus 1190 meter. So that becomes 9017. Then we have this 1 meter. So the distance between those it 1870 meter, right? Almost 2 kilometer, we can say almost 1.87 kilometer or almost 2 kilometer, right? Very long distance. Therefore, he was able to hear some echo there. Okay, so this is also one of the important question. So check this one. You have to solve such type of questions, more questions. Okay. Then there is one more question. Actually, we have solved this type of question in the previous session. So I'm going to give this you as homework. So what is the question? A stone is dropped from the tower of 500-meter high into pond of water at the base of tower. So we have solved this question actually. So consider this is the water from the top of tower which is 500 meter high. Stone is dropped like this, right? So there are two cases, right? One, it will stone have to go downward. Here you have to use what? Kinematic equations. And when the sound is coming upward, so sound will also need some time to come up, right? Let's call this as T2. Here we don't have to use the kinematic equation directly. You can use T2 is equal to distance upon velocity of sound, which is given. Distance is also given, right? So when the splash is heard, means you want to calculate T1 plus T2. So we have actually solved this type of question. So I want you to do this, right? Okay. So anyway, this is the whole chapter of the sound, and I hope that you understood this chapter, this concepts, and very nice, right? Very nice concept that is sound. Okay. So in the next standard or 11, 12, we are going to study this chapter that is sound in detail. There will be some equations, a lot of numericals will be there. So some basics formulas we have already seen in this chapter. I want you to solve as many questions, as many numericals on this, right? And if you do have any queries, just put them on the forum so I can answer them as soon as possible. Okay. So anyway, we'll stop here. Thank you very much. Have a nice day.